This is a graphical image showing a transition between solar cycle 23 and solar cycle 24. Here we are right now just at the end of solar cycle 23, ready to start 24. And what happens is the sun across an 11-year sunspot cycle changes the intensity of the energy it produces very slightly. Here's at a solar minimum in 1996. There's hardly any sunspots. And then here's a solar maximum right here. Here's one from 1999. You can see these little sunspots here. Now, when there's an increase in sunspots, there's a slight increase in the amount of energy which the sun produces. And it throws that energy out into the solar system and strikes the Earth. And here it is right here. This is the energy change across this is from 1978, 88, up to 1998. Here's the peak. Here's a trough right here. The sun's output varies by about 0.1% or 1.4 watts per square meter across an 11-year sunspot cycle. Problem is, and this is the problem that has been with all these research papers, the hundreds of them literally, through the years that saw this correlation between the sunspot cycle and apparent, sea surface temperatures and between global temperature anomaly and so on, is that that's really not much energy. 1.4 watts per square meter across a sunspot cycle will not drive the climate change that we see. If you're going to have climate change, you have to have some kind of amplifier. And this is where everybody has been stymied for years, until very, very recently. Now, this is a nice graph right here which basically shows the solar wind. And that solar wind is coming from our sun, and the solar wind slightly varies a little bit across a sunspot cycle. As you move to the peak of a sunspot cycle, there's more energy being released, and that enhances the solar wind. Now, counteracting that, our solar system is continually being bombarded by cosmic rays. Cosmic rays are stripped-down neutrons, which basically come from supernova within the galaxy. So these are basically continually bombarding our solar system. And and again, they're trying to get to the inner part, but they're being deflected by the solar wind. During a peak of a sunspot cycle, more cosmic rays are deflected, but some still get through. So when you have a trough in a sunspot cycle, more of these cosmic rays get through to the solar system, and when you have a peak of a sunspot cycle, the solar wind is stronger and more are deflected. And the question then arises, so what? What does that have to do with phytoplankton production in the Northeast Pacific? What does it have to do with Pacific herring or anchovy, or the amount of rainfall which creates the dark layers that we see, and so on? So let's look at another part of the equation. Clouds are important controls over climate in our planet. Okay, so cloud basically has two effects. Clouds can either result in greenhouse gas, or basically they can act as a blanket which makes the planet warmer, or they can reflect solar energy back out away from our planet and result in a cooling. Now, the result is that our overall planet, when you have more clouds, there's a cooling going on. So the more clouds, despite there be some result in a warming, some result in cooling, the overall effect is when you have more clouds, you end up with a cooling of the planet. And so the question then is, so what? Again, what do clouds have to do with my anchovies and my phytoplankton? What does it have to do with cosmic ray flux and so on? Well, here is the so what. Here's an interesting correlation that has been measured between low cloud production, between solar irradiance and cosmic rays. They match up perfectly. And this has been a measured phenomena. This is not hypothetical. This is actual data taken from a paper by Carcel et al. In 2002. It ends up, the correlation has been that they recognize that more clouds, more cosmic rays seem to result in more clouds and lower temperatures. And in fact, it's been measured that there's something like a 1.7% variation in low cloud formation between a solar maximum and minimum. So all these three things match up. And so the idea was there must be some kind of, the cosmic rays must have some kind of impact that result in the formation of more clouds. But there was all kinds of hypotheses put out as to why this might happen. And Interestingly, a landmark paper was just published in the Proceedings of the Royal Society in October of 2006 by Svinsmark, and they have finally experimentally demonstrated how that happens. How cosmic rays excite electrons and result in forming more cloud nuclei. So we now, and this has been a problem with this hypothesis as a climate driver, is that they really didn't have a mechanism for it, or they had the mechanism, but they didn't have proof. Now they have proof. So let's look then at how this all fits together. The so what between my fish production, my phytoplankton, the clouds, the upwelling, and cosmic rays. See how it all impacts climate. So here's the idea. We have our solar system continually being bombarded by cosmic rays. Cosmic rays enhance cloud production on the Earth. The more clouds that you have results in less solar energy getting through to the Earth's surface and an overall cooling. Counteracting all that is the solar sunspot cycle. During the peak of a sunspot cycle, we end up with more solar energy, or more solar wind, which deflects more cosmic rays. More cosmic rays deflected, we end up with fewer clouds. During a trough of a sunspot cycle, we end up with a lesser amount of solar wind, more cosmic rays get through, resulting in more cloud formation and overall cooler conditions, resulting in this graph that we see right here. So this is a smoking gun to explain what's happening. And in fact, the cosmic ray intensity varies by something like 15% across the sunspot cycle, which causes that 1.7% variation in cloud formation. Now, the interesting thing is, that's an 11-year sunspot cycle. As we ramp up to larger sunspot cycles, here's the Gleisberg cycle, the Seuss cycle, and so on, that it varies by a factor of 3 to 4. So we end up with a massive change in the percentage, the amount of cloud formation when you move up to these longer solar cycles. So they can have a profound impact upon climate at that point, not just relatively minor impacts. So here is the model which I think controls what we see. But before I do that, I want to show another interesting correlation. There's a paper by Hamid and Lee in 2003 at the American Geophysical Union. They looked at looking at the sunspot cycle, and they correlated with the center of formation of, or center of action, the place anyway where the Aleutian Low and the North Pacific High form every year. These are annual things that they disappear. The North Pacific High largely disappears in the wintertime. The Aleutian Low largely disappears in the summer. So they form every year. But where they start to form varies every year. What they found was there was an interesting correlation between the center of formation of the North Pacific High and the Aleutian Low and the sunspot cycle. And this can start to have an impact, because you think about, well, the North Pacific High controls upwelling, which my phytoplankton love. So if you have the North Pacific High just sitting in the very right spot, in the sweet spot, so to speak, you'll end up with enhanced upwelling and more of my diatoms. And as it moves around, it may move at a different part of the sunspot cycle to a center of formation which is not so nice, and we have less upwelling. And so this is what I think we're seeing.